yeah, so this will be the final lecture before the tutorial this afternoon, which will also be on this next video on listings. So let's recap a bit what we did so far. So we started by can you maybe turn off the lights? Thank you. So we started by looking at I had this little example of the Rally production to show a bit what we were doing, and we had this leading order contribution here, and then we were very much busy with computing this maximum leading order corrections, right? We had the real division corrections and the virtual corrections there. So in the first two lectures, basically we discussed the traditional method of computing the loop, this loop integral here, using this Passerino-Beltman reduction. And in the second lecture, we had this more efficient new techniques, which we call the OPP reduction technique, to compute the same loop integrals, but only in a numerical kind of framework. So yesterday, in the third lecture, we started to include this real mission corrections, and basically because we know that the poles, the infrared singularities between the contributions here and between the contributions here should cancel. We had a way of this slicing method or a subtraction method to explicitly factor out the poles of the real mission correction over coming from the phase space integral over this gluon here. So we basically did everything to get results for a fixed order calculation, and we can make predictions for the next leading order observables, and observables and next leading order accuracy. But not all observables, only observables which were infrared safe. So, because I had this question yesterday, just before I ended my lecture, and maybe there was a bit of confusion, I had included one more slide on how we actually do this in practice. Right? So in practice, we want to do these phase integrals numerically with Monte Carlo integration. So we have these contributions, right? We have the Born contributions, the virtual contributions, the real mission contributions, and then these subtraction terms to get rid of the singularity, to factor out explicitly the poles in the real mission singularity, so that this pole structure is finite. And then here we get the poles explicitly because we use one Python phase space integral analytically, and then also we can cancel this with the poles in virtual corrections. So in practice, we do these Monte Carlo integrations numerically. So if you look here, this integral and this integral are exactly the same. So normally we combine these two together, but you don't have to. So you can do these integrals all independently if you want. So what we do is we generate two sets of momenta when we do the Monte Carlo integration. An n-body set, which you use for these two contributions, and an n+1 body set, which you use for these contributions. Now, the contributions here have slightly different momenta compared to the one here, because in this term, we have to set explicitly the energy of this particle, this extra particle, or the angle between this extra particle and another particle to zero, to cancel the singularities explicitly. Right? So therefore, I put a little bar. So we generate an n+1 body momenta, but then we map this n+1 body momenta to the momenta of the counter here and use it here. So and then we compute. So we have this phase space point. We compute the matrix element of this phase space point. We apply cuts, or we apply cuts directly on the matrix on the phase space points. If we say, well, we want to have a jet with at least 20 GeV, we say that all the momenta we generate in this way have at least this 20 GeV. And then we compute these matrix element contributions, and we fill the histogram at that particular point with the weights of these contributions here. So this way we fill our histograms directly when we do the integration. So this is how we do this in practice. Then of course the bin in the histogram that we fill depends. It's defined by the set of momenta that we use here. So they might be different for this n body set momenta or this n+1 body momenta, but also they might be different between this contribution here and this contribution here, because these have slightly most impressive next leading order calculations is this one here by Virgil et al. Part of the black hat collaboration together with Sherpa. These are the codes that we use to compute this calculation. And this is W plus 4 jets in next leading order. So what you see here is the transverse momentum of the. So when you generate such a process, you have to define that you want at least 4 jets in your final state. So you say, well, all of my jets must have at least 25 eV, so I have 4 jets of 25 eV. You put a cut on the pseudo rapidity and some cuts on the decay products of the W boson. And what is plotted is the hardest jet, the PT, the transverse momentum, second hardest jet, third hardest jet, and the fourth hardest jet. So what is now and then they plot both leading order and next leading order. So you see that the differences between leading order and next leading order are actually quite small. Right? They are almost on top of each other. But it's kind of deceiving because the uncertainty in the leading order calculation is this hashed dash here, while the uncertainty in the next leading order calculation is just this small grayish thing here. Of course, you see some statistical fluctuations, so you probably have to think it's slightly larger than what they show here. But this is the way it works, right? So you have the leading order scale uncertainty, leading order uncertainty. So the uncertainty in your leading order calculation is much larger than the uncertainty in the next leading order calculation. So that is the power of next leading order, right? So you go from a prediction with a large uncertainty, which is now if you look here, it's almost 50% up and down. You go to an uncertainty which is maybe 10% up and down. So this is what you get. Now there's one more thing that is the topic of today's lecture, and it is if you look at observables like this. So we go back to a little simpler example of just 1 W boson plus 0 jets, and we compute the next leading order calculations. But then we plot the PT of this vector boson. Now, at leading order, that's just this diagram. The PT of the vector boson is just 0. So we get 1 bin at 0, which has been filled by the PT of this by the PT of this vector boson. And the height of this bin is then exactly the cross section at leading order for the Young production, or the W production. Now, if you could include next leading order corrections, also these virtual corrections will enter the same. So the Born will go still. The Born contribution to the next leading order calculation will go still in the 0 bin. The virtual corrections will also go in the 0 bin. But these real mission corrections, they will go away from 0, right? Because in this real mission corrections, the energy of this transverse energy of this little part of here is non-zero, and therefore you get a distribution like this. So the total rate is given by the total. The total next leading order cross section is just the integral over this variable here. So this is if you sum all these bits together, you get the total rate. However, you see something strange going on here at 0, right? Because you get some negative bin, some negative contribution. So how should we interpret this little instability problem here? Now, this you get because this is not an infrared safe observable. So that's why we get this nonsense prediction here. But we can easily understand, right? Because if we just to get a non-zero PT, we only get contribution from the real mission corrections here. And we know that those diagrams diverge with the PT of this particle goes to 0. So if you make this bin smaller and smaller, we get a larger and larger peak here, but then the dip at 0 becomes also more and more negative. Right? Because we know that in the end the poles are going to be cancelled by, so the singularity itself is going to be cancelled by the virtual corrections here, which just have different, which are just sitting at 0. And this is how we interpret this. Now, so we have really some problem here. However, this region of phase space, where partons are very soft or collinear to initial state partons, are the region of phase space where the parton shower does a very good job. So what we want to do is somehow match this process here to the parton shower at the next leading order accuracy. So that will be the topic of today's lecture: how to matching to the parton shower at next leading order accuracy. Yes. So parton showers offer this summation of these large logs in this region where this fixed order next leading order calculation has this instability problem at low transfer momentum. Furthermore, they offer a realistic framework for heteronization, and therefore we can really deal with physical observables, physical hadrons, and pass them to detector simulation and all that kind of business that Johan also advocated in his lectures. So I actually took a slide from Johan about this MLM CKK graph, basically about MLM matching and why we want to combine matrix elements and parton showers. So all these reasons why we want to combine them, so that why they are complementary, are still true, except for one of them. If we do, still true at the next leading order, except one of them, and that is this one here. So the next leading order matrix elements are also valid when one of the partons is not hard or well separated. Right? Because if we do an next leading order calculation, we need to integrate over the full phase space of this one parton here, because that only if we integrate over the full phase space, we get the contributions to the singularities, the contributions to the poles, which we need because they need to be cancelled against the virtual corrections, right? Virtual corrections have this infrared and collinear poles, and they need to be cancelled. And the only way that we cancel them against is when we integrate over the total phase space of this gluon here. So at next leading order, it's no longer true that all partons are hard and well separated. So, and this brings a whole complication in how we do this matching procedure, because we cannot use the same prescription as we were using for MLM and CKJW, where we just factorize the phase space and we say if the parton is soft or collinear, we should use the description of the parton shower, and if they are well separated, we use the description of the matrix elements. Because now, if this one is soft or collinear, we should still use the description of the matrix element and not the description of the parton shower. So we have to invent kind of a new way to do this matching between matrix elements and parton showers when we use matrix elements the next to the point. Yes?
So when you consider any role, because of the virtual correction, you consider the matrix element rather than the parton shower.
Yes. Yes, because the virtual corrections have this divergences in them, and they need to be cancelled, and we can only cancel them when we include real mission correction. And that also means that we have to integrate over this part of space all over the region. Also that goes completely solved.
So the parton short description doesn't go correctly for the initial phase.
We have to play a bit with what we do to get the correct result. So that's the topic of this section, to explain to you why the naive approach, which will be our next slide, is not the best approach that we think. So let's start. In a fixed order calculation, we have contributions from the M and the M is one particle phase spaces. So as basically this equation here. Right? I suppress the subtraction terms, but they don't, to cancel the singularity. That doesn't help us if we include them. So what we could do is just shower them independently. We could say, well, this is all n part of phase space, and this is n plus 1 part of phase space. So if we just use what is coming out of this equation here and what is coming out of this equation here, and just shower it, what will happen? So in equations, it's kind of a bit difficult to for the initial state condition. So if we take the Born here and we multiply it by the shower thing, it's just, you take your Born events and you shower them. Just what MGraph is doing. And this depends on the number of sparkles that you start with. Right? So what we can just do is try to shower the M and the M+1 final states independently. So we do some matching next to the order with Python shower, like this, for a given observable.
While you're showering, you begin follow the matching procedure, right? Because this phi which you shower, it would be exactly like R phi n plus 1 and some momentum.
So I don't understand.
I mean, it's the same overcomping problem I'm talking about. When you're showering, the Born process and the last one. So
exactly, that's why this is written wrong here. Naive, which is wrong. So this is not this indeed that you already found it. But let me continue. So if you just use this we start from the Born phase space and we multiply it by this operator. This means that we use these momenta that we get out of this calculation and we shower them and then we look at an observable pole. And we can do the same for the real mission. So this is our naive approach, and in the next slide I will show you why this is wrong. So this is wrong. Why is this wrong? Because if you expand this equation up to next leading order, there are more terms than there should be. And even the total rate does not come out correctly. So schematically, this operator O for just 0 and 1 emission is just given by this pseudocovector, right? So for 0, if there are no branchings, that means that we should just this operator here is proportional to the no branching probability. And if we have one branching, for example at D, we have the no branching probability between the hard scale cube going down to D, and then multiplied by the probability that we have this branching, which is written by this splitting function here. Right? So this is the same pseudocovectors as we've seen in the lectures on Python showers. Right? But that is exactly what the Python shower does. That is what I mean by this little operator here. So this is pseudocovectors. So if we now plug this into here, and we expand up to next leading order, so we keep all terms which are just one order of alpha s more than the Born contribution. What do we get? So let's start from this side here. So the Born is here, but let's start from the real. The real vision has already one more power of alpha s compared to the Born. Right? So we just have to expand this one up to the lowest order. And the lowest order is lowest order in alpha s, and that is just 1, right? Because this is an exponent here, this is also the exponent, so we start at 1. So we get a contribution from 1. We can do, if we expand the exponent, we get 1 plus 1 minus something. So this is just 1, and this already starts at order alpha s, so we can get this contribution here. So we just have the real emission contribution here. If the same for the virtual already has 1 power of alpha s more than the Born, and therefore also this one we can just approximate by 1. Only the Born will receive a contribution which is just more than 1 for this operator here. So if we expand this to order alpha s, this term already has an alpha s here, so we just take again the lowest order contribution from delta, and the lowest order contribution from delta is 1 as I just told you. So we have this, plus this term here. But then this one here, we have to expand up to the first order in the exponent here, which is just the argument of the exponent itself. Right? So we can easily see that we get that this term here does not cancel against this term here because there's an explicit integral. Right? So these are not the same, and also the dependence on the integration momenta is not the same, even though they enter with different signs instead of minus signs. So there is an extra contribution here which does not cancel. So we know for sure that if we do this naive approach here that we get something which is not visible, it's just not correct and actually not. So this is a bit of a complicated way of describing it, but there's actually a simpler way with kind of pictures. So suppose that I just denote the Born plus the virtual conclusion with this diagram here. I just use the same diagram because it's the same, it just depends on the final state stuff itself. And I can do the real mission here. Now if you then start showering, I get this. And the shower will continue, so you get more stuff and so on and so on. And then of course you get the same kind of double counting as in the MLM approach and the CQKW thing. That is that this partly shower emission here is overcounted because it's already there in the real emission. And also this one here is already here, and so on. So you get all these double counting problems here. So there's all this double counting. There's actually another overcounting which is not really clear from this picture here, and which is due to the fact that the virtual corrections themselves overlap with the pseudocode form factor. So we can have a look at that, how that works, and that is the following here. So this pseudocode factor, which I've written down here on this slide here, is the no emission probability, right? So it's defined to be basically 1 minus the probability that the branching occurs, and then all the possible branchings. 1 minus 1. If no branching happens, then So it's probability that there's no emission, and therefore it's defined to be 1 minus the probability that there is an emission. So that's just the conservation of probabilities. That's kind of trivial. However, this probability that there is an emission is a pure real emission kind of thing. But by saying that we have conservation of probability, implicitly you get contribution from the virtual corrections. Right? And the reason is that, for example, that we need to cancel infrared singularities again. So the probability that we have an emission, if this emission is very soft, this pole needs to be cancelled by some virtual corrections. And by defining it in this way, by saying it should always be unitary, it should always be conservation of probability, we get implicitly information on the virtual corrections. So because if we do an explicit next leading order calculation, we already include the virtual corrections by their diagrams, by the loop diagrams. We get a double counting between the virtual corrections and this pseudocode factor. And in fact, if you think about it a bit more, because the shower itself is unitary, so what we double count in the real emission corrections must be exactly equal as what we double count in the virtual corrections, except with an opposite sign. So this double counting that we saw explicitly here, the same kind of double counting with the same magnitude happens between the virtual corrections and the pseudocode form factor. So what we can do, and this is what the so-called MCA10LO procedure, which was invented by Friccione and Weber in 2002, if I'm not mistaken, is to explicitly remove this double counting from my equation here. So if we remove from the real emission exactly what the shower would do to get to the same configuration as real emission matrix element starting from the Born, and add the same thing back integrated over this one particle phase space to compensate for the fact that in the pseudocode factor it has a similar virtual correction as explicitly in the matrix element here, we get something which is exactly what we should not have any double counting here. So this double counting here is explicitly removed by this R minus MC. So instead of just starting the shower from this real mission matrix element, you take this real mission matrix element, subtract this part here, and then start the shower. And that means that in this term here, where we subtracted this one, the shower part starting from this configuration here is already excluded because you just put it back in here. Right? That is why this works here. And similarly for this virtual corrections, which is overcounted by the pseudo factor, we have to add these contributions back in. So that is how this MC NLO procedure works. So some of these properties or features of this Monte Carlo subtraction terms, as they are called, these MC terms, are the following. So the double counting is avoided. There's a smooth matching, and it's there is stability. So I'll have a slide on each of these three, so in a bit more detail, so I'll show you what I actually mean by that in the next few slides. There's one not so nice feature, and that is that these Monte Carlo terms, because we want to cancel exactly what the shower is doing starting from a given configuration here. So we want to cancel this exactly what the shower is doing. The form of these terms, these MC terms, depends on the part of the shower itself. Right? That means that for each part on shower that we want to match to in the next linear order calculation, these terms will be different. So if you want to use Pythia, it's going to be different than if you want to use Herbig, or we want to use Sherpa, or we want to use, it really depends on what shower we want to match. So that is really the not so nice feature, because that means that we have to work hard and define exactly what the shower is doing and get this result explicitly there in such a way that that we can match not only to one of the showers but to all of them. So for each of them we need to define them independently and write them down and implement them into a computer code. But let's have a look at these three good things that allows us actually to properly match linear order calculations to a Monte Carlo tool. So first of all, the double counting is avoided. Right. So I showed you already this operator, what it actually means. So if you expand this to next leading order, the definition of this Monte Carlo term is exactly that the expansion of this one here is this one, is defined this way. So the notation is kind of a bit of amusing in the sense that this is the probability that there is no emission, and this is the probability that there's one emission. So this corresponds to font in this equation here. No emission probability plus the probability that there is an emission. And the difference is really in this one interval here, which happens here, well, this interval is not here. We expanded it or the half-mass. So that's why I wrote it in this way. There's the integral here, but the integral is not here in this term. So now if you plug this in here directly, you see almost immediately that what we get is true at next leading order, right? Because again, if we expand toward alpha as this one is just 1, so we just ignore it here. And if we expand this one toward alpha as, we just have to include this one and this one, and when we multiply by the board. So we cancel exactly with this term, we cancel exactly with this term here, because we multiply by the board. And this term cancels exactly with this term here. So we get that the total rate is preserved at next to the order. Furthermore, there's a smooth match matching between the hard region, where we trust the matrix elements better, and the soft region, or collinear region, where we trust the Monte Carlo, where we trust the Barton shower Monte Carlo tool much better. So to show you that that is working, you can just take the limit to the two regions. So if you take the limit to the soft and collinear region, then the real missing matrix element is very well approximated to what the Barton shower does. Right? That is where the Barton shower approximates the matrix elements correctly. In the limit, the splitting function is exactly the same. The Born times the splitting function is exactly the same as the real missing matrix element. So in this limit here, this term here just drops out. And so in the soft collinear region, we just get the n-body contribution times the Barton shower contribution here. So, which means that in the soft collinear region, we do exactly what it should be have exactly the same shape as Barton shower gives you starting from an n-body configuration. On the other hand, in the hard region, where we want to have the matrix element to do that better job, this also is true because in the hard region, the Monte Carlo term is defined to be 0, and the reason for that is that also this operator here is going to be 0 because the Barton shower should not give any radiation, which is very hard, which is hard, which is not soft and not collinear. So therefore, this term is basically 0. So all this first line already drops out. This Monte Carlo term is also 0 because of the same reason. So this also drops out. However, if we start this operator from the one particle extra, this should be almost 1 because we start already from the configuration where we have an extra hard particle. So this is almost 1. Therefore, in this hard region, the prediction of this MC8NLO is very close to this maximum order matched with the Barton shower, is very close to the real emission of the phase space measure. Alright, so we have by just taking these kind of limits, we have a smooth transition going from the soft and collinear region where we trust the Barton shower, and we get the correct shape of the Barton shower, to the hard region where we get the correct shape from the matrix elements. Right? So the third good point was the stability issue, and that is actually a very, very good point, and that is the following. So this Monte Carlo subtraction term, they were defined to what the shower does starting from an n-body Born process to go to an n-body, n+1 body process. To get the same kind of phase space configuration which you have in the real mission. So this Monte Carlo term here is actually a function of the phase space of the real mission and the exact same phase space of the real mission. So it's different from the FDS subtraction, where we had dependence on the counter terms, which was the phi bar phase space. But here it's exactly the same phase space. So the cancellation of the singularities is even more precise or more exact in this term here than the equivalent term we had in the FDS subtraction. So that means that in fact this integral here is bounded all over phase space, and we can therefore generate a Murray dependence. These terms between brackets here are bounded, and we can integrate them independently, and in general we do integrate them independently. In fact, we have to, because we later on have to multiply, well, the particle shower works differently with both of these contributions. So we generate what we call S events, which are coming from these contributions, and H events, which are coming from these contributions. Why are they called S and H? Because usually these S events correspond to things which are kind of soft, while the H events correspond to things which are hard. The hard emissions are this is the soft and collinear stuff. So that's very nice. That's very nice. So we can generate these unweighted events here and pass them. First generate event and pass them later on to the shower because we have this exact phase space between the real and the Monte Carlo. So there's a better cancellation as we had before. So do we still need the FES subtraction? Because now this part is finite and this part is also finite independently. The answer is actually yes, we still need it. And maybe somebody will see where in this equation we will still need it. So I'll give you 1 or 2 minutes to think of it. Somebody has an idea? No? The reason is the following. So, here we don't need them anymore. This is finite. But here we still need them. This integral here is way too complicated to do this analytically. So in fact, instead of doing this integral analytically here, we use the subtraction method to cancel the singularity here and add them back in again to factor out the poles in this term here, because they have the same poles as the real distance. So we can use the same subtraction terms as we had before and add them back in with the virtual fractions together. So we still need this FES subtraction method right here. And now you might also see why FES subtraction is maybe more efficient than is kind of efficient in the sense that because it starts from the collinear picture, you're always looking at you start with 2 partners going collinear. And that is the same what you do in the Monte Carlo terms. The Monte Carlo also is exact in collinear branchings. You get a better, you would prefer to use this kind of similar structure for these subtraction terms here, because that just helps bookkeeping and all that. You know, I mean, in principle, there's no reason that you should use FES subtraction. But in bookkeeping problems, it helps because the Monte Carlo terms arise from a collinear picture as well as this FES terms, which arise from a collinear picture. So this is where we still need the FES subtraction. So there's actually one more kind of complication when we do this kind of when we want to implement and study this process, which is actually more matched with the final shower using MC8NLO prescription. And that is that we do kind of these integrals independently. So there's no real guarantee that for that these separate contributions are both positive. We know that for a final observable, an infrared safe observable, we should get a positive prediction. But if we split the calculation into 2, there's no guarantee that these separate contributions are both positive. So, in fact, in general, they are not, because you already see it here from this minus sign. So if this Monte Carlo term, the finite contributions, so which are away from the poles, are larger than the real emission corrections, this term will be negative. Therefore, we have to integrate the negative integral, so we always get negative contributions to our final event sample. We get events with negative weights. So this event unweighting that we're doing, we cannot unweight exactly. We can only unweight up to a sign. So all our events in our event sample have the same weight, but some of them come with a positive sign, and some of them come with a negative sign. So of course these signs should be taken into account when doing a physics analysis. You cannot just throw them away or keep them all positive or change them all positive. You have to keep the sign into account to be sure that the contributions are correct, so that the final equation is correct. So that also means that if you use a very low statistics, you might get observables which are bins which are negative, right? So you always have to make sure that you generate enough events to circumvent this problem. there's no, you can prove that for infrared safe observables, if you use enough statistics, you always get a positive prediction. So you have to use enough statistics. So this is how it works. So let's summarize this part. Let's make this one summarize this part. Yes. So we want to match mixed linear order computations to Parkin showers to keep the good features of both approximations. Right. The next linear order has a small theoretical uncertainty, so we get good descriptions of total rates and distributions which are kind of hard and well separated. And then the Parkin shower does a very good job when Parkins are soft, and also they have a very nice model for including hadronization effects and non-perturbative physics. So we want to combine both of them. So by including these extra terms, these shower subtraction terms in our integrals, we can avoid double counting between the next linear order process and the Parkin shower. So this is the MCA Danilo prescription here. So these counter terms have exactly the same dependence on the phase space as the real mixing corrections. And therefore the difference between the two in this equation here is always finite, and its factor is always bounded. So therefore we can do unweighting components. However, we do get negative integrals, so we can only unweight up to a sign. We get positive and negative events. But observables will always be positive if we have enough statistics. And so recently, all these contributions that I've been talking about in my 4 lectures have now been automated in the MATLAB code. And we decided not to call it anything with NAT, but we just called it automatic MCA. So it's not a NAT MCA or something like that. So we have a little website which is called amcfnlo.cern.ch. And on this website you find the latest news on this computer. So you find many slides of many talks given on this course already. You also find event samples. So you can go to this website, download an event sample, and ready for showering and analysis there. So you can use the results from this code already. However, the code itself is not yet public. So our tutorial can unfortunately not be on this code. But we use, on the tutorial this afternoon, we use the other code, the original code by Fri3 MGraph, which is called MCA without the automatic A. But before stopping here, I still have 15 minutes. So what I want to do is I want you to show some recent results. There's one thing that I should mention here. If you're doing a loop calculation yourself within the standard model, we have now, very recently, since I think it was since last week, we have this very nice feature that you can check a single phase space point for a virtual that you computed by hand or with some other code, and you can check it against our MATLOOP code. So if you go to our website, you can type in any process in the standard model you want, and it will give you 1 or 2 phase space points for this particular process. So this might be useful for theory students who are doing their own virtual computation, virtual corrections, and so they can make comparison and check against our code. And maybe find bugs in our code, right? It's always possible. So you'll be very happy if you test your own codes. And tell us if you find something which doesn't make any sense. So the last 15 minutes or so, I want to show you some of the recent results we have obtained with our automatic MCA code. And as you can see, we have written 4 papers on this code so far, all of them with the same collaboration. And all of them are very recent. All of them are this year. You can see here from the archive number that they all in 2011, 1 in April, 1 in May, and 2 actually this week. So I just picked out one of them, which I'll have a few plots so you can see what what are the difference between a fixed order next leading order prediction and code which is matched to a Python shell and compared to leading order and leading order with Python shell. And that is this 4-charge step from production and Halo colliders. So what you see here in this plot, there are 4 curves. There's the leading order prediction in this, if you look very carefully, this dashed magenta line. There's the blue line, which is what we call AMC at leading order. This is just the leading order prediction, which we pass through a Python shower. So this is just MGraph plus Python shower. In this case, it's always Hurry that we use. So sorry, not always. This is Hurry that you see. Then we have the fixed order next leading order result in this red dashed line. And then we have the AMC at MLO prediction. So this is the next leading order matched to the Python shower. Same curves. In this left plot, what this represents is the invariant mass of 4 charged leptons. So if you look here, so if you think about what kind of diagrams contribute here, then it's actually diagrams like these, right? So you can have a Q at Born level Q to bar is a state, and we can have, for example, the Z here, which decays to E plus E minus, and another, so Z gamma star, another Z gamma star here, which then decays to U plus U minus. So there are diagrams like these, right? These are the contributions. There's another set of contributions, and that is, so these are the bulk of the contributions. This is really, the peak region here are all coming from contributions like this. You see another peak here, which are not so much coming from contributions like this, but they are more from things like these. Let's say you can have a Z for gamma star, and then you get to a E plus E minus, and then you can have another Z here, which goes to E plus. So the invariant mass of these 4 leptons are going to be peaked at the Z peak, and that is this peak. Right. So, what you see here is something where you would say, well, there's a difference between leading order and next leading order, but there's no difference whatsoever between leading order and leading order with Python shower, nor between next leading order and next leading order. That's exactly what you would expect, because an invariant mass of 4 leptons will not get any contributions at all if you include, extra radiation coming from the initial states. Right? So this is something that you would expect. In this right-hand side plot here, you have another observable which is kind of maximally sensitive to what the Python shower is doing. And that is the transfer momentum of the 4 charged leptons together. And then you take the logarithm of it, because then it's nicer as well. Right, so here is the transfer momentum of 100, here's of 10, here's of 1 GeV. So now at leading order, without any Python shower, the dt of this 4 lepton pair that I've drawn here is exactly 0. So therefore, if you look here, this line doesn't enter any of the plots, because at 0 the log of 0 is minus infinity, so this line is not there. You don't see that in the plot. Now if you start including Python showering, then you always get initial state radiation, so you always get a non-zero dt for your 4 leptons, and therefore you get a curve like this. Now at next to leading order, you get always, in the real mission, you get always an extra particle. So, but that matrix element diverges. So you get this divergence here, which is then cancelled by a bit at minus infinity, which goes which goes below 0. As we have seen in this little plot that I showed you at the beginning of today's lecture. Now, then we have the final contribution, the final result, which is next leading order with Python shower. So we get a good feature of the next leading order here, that in the hard region, we agree with the fixed order next leading order calculation, as we should. And while the leading order really exactly the same as what the Python shower does at leading order. Normalization is still different because we still have the next leading order normalization. But in shape, we do exactly what we should do. And therefore, it's a better prediction in general than leading order with Python shower. So you see here the smooth matching between the next leading order results in this region here, and then the leading order results in this region. Now, in these insets here, you see you have a ratio coming from the fractional scale uncertainty. So this is the leftover dependence on the unphysical parameters that enter next leading order calculation. So, and this is an estimate of the uncertainty in the final result. You have the scale uncertainty, which is due to the renormalization and factorization skills, and there's the PDF uncertainty, which is due to the PDF sets that go into the calculation. The Python distribution functions. Probability of finding a Python with a given x in a given energy at a given scale, let's say. There's also an uncertainty associated with that which you can compute. And this is the uncertainty at the next leading order. So it's kind of flattish all over the range. While here, the next leading order matches the Python shower. While here it's no longer true. It's not flattish. Well, it's kind of flattish here, but then here it blows up somehow. Not blows up, it just increases. And the reason is, it's actually kind of interesting. And the reason is that out here, this next leading order prediction is actually kind of leading order, right? Because we really need this extra jet, this extra particle that enters in the real mission. So this extra gluon here, and the real mission corrections to be very, very hard to get us out here in this very hard PT for this system. So here, in this region of phase space, there's no cancellation between these contributions and the virtual contributions. And only when we have this cancellation do we have the reduction in the scale disturbance. So therefore, this grows here enormously. And this region, all this region, there's contribution from the virtual as well as from the real emission, because the Python shower shifts the virtual corrections from the 0 PT grid to the non-zero. So and then we showed a few more plots. So you see again, this is something. Yeah. Sure.
Is the trend for this PP distribution between leading order and the next leading order similar for single zero-sum production? Like just two vectors?
It's the same.
It's very similar. So
yes.
Large PP, it goes along with the NAO prediction.
Yes.
But in medium,
it
goes above the NAO, and then at low, of course, it goes down.
Mm-hmm.
Now, for Z plus longit, you can still do NAO at MC at NAO. If you do that, what happens to this high PP region, and whether you can smoothly connect the two curves? But by combining MC at NAO for Z boson plus anything which corresponds to this, and then you can also do Z boson plus longit. For this process, you can do MC at NAO. And if you do combine this cleverly, just like not this matching, probably you can connect it at the NAO accuracy. And then, of course, at very high peak detail, the scale sensitivity becomes smaller.
Yes.
Have you done that?
So to combine a Z plus 0 jet sample at next leading order matched to a Python shower, does it together with the Z plus 1 event sample matched to the Python shower at next leading order. It's very difficult.
Very difficult.
Actually, it's not. There's only been, two or 3 weeks ago there has been a paper where the first tries have been really worked out. Yeah. So we have not tried this yet with our code. We are thinking actually about another method of doing this, which is still kind of work in progress. So there's still work to do to combine these two samples consistently. But indeed, I would expect that if you combine them properly, you get also a small scale uncertainty in this region.
Yeah, if you are successful.
If that is possible, yeah, if you can do that.
Do you mean that there has been somebody else who could do it, or?
Yeah, so there's Keith Hamilton together with Paolo Nazon, and
so they used Pohek?
they use Pavek, and they have the first results where it matches Z plus 0 and Z plus 1.
How does their result look like?
But they haven't shown this plot. So and moreover they don't use they never have provided plots with scale uncertainties. And the reason that is that is kind of difficult for them is that normally what you do to compute scale uncertainties, you make your distribution, you change the scale, you redo your whole calculation, and look at the difference, and that gives you a scale uncertainty. So you have to do many, and then you have to do many scales because you have the factorization scale, the renormalization scale. You want to change them independently to be kind of conservative. So you usually do like 7 or 9 different runs, and that gives you the scale uncertainty. So it's a lot of computation that you have to do. Now, in our code, we have a kind of a clever trick to do these kind of scale uncertainties because the dependence on the renormalization and the factorization scale is known analytically for any process. So by saving intermediate results for the events, you can actually later on reconstruct the dependence on your scales with the events you got. So you can somehow reweight your events and use this to compute your scales. So for us, getting these kind of plots is kind of not really next to
used by anybody.
So they can be used by
yeah, I mean, that's one thing can be done by anybody.
Yes. If they want, but it's kind of you have to be careful to do it correctly. And they haven't done that yet, so they have not provided any skills.
Okay, thank you very much. Yes, I really wanted to go.
Okay, yes. So given that I'm running out of time, I have this other plot, which are basically the same observables here, except that now we compare Hurwig with Pythia. So Hurwig is the solid line, and Pythia is the dashed line. Again, for this, so forget for the moment about these symbols, these curves here. Only look at this line. So these are kind of the same as we had before. So again, the difference between Hurwig and Pythia is negligible in such a distribution here, because the same reason as the fixed order is the same as the fixed order plus Parton shower, and the reason is that the Parton shower doesn't change the infinite mass of 4 leptons of such a final state. But again, if you look at this log of the Pt of this pair, you do get a large dependence on your Parton shower in this region here, because this region is extremely sensitive to what the Parton shower is doing exactly. So that's why you get a larger dependence on your Parton shower in this region here.
So which one is
Actually,
Pythia? Which one is Pythia and which one is...
So Hurwig is the black line and Pythia is the blue one, the dashed blue one. So it's the difference between this line here, which is the black one, and this line here, which is... So this black one is Hurwig and the Pythia is the blue one. So these symbols here I should not look at further.
So Hurwig has stronger Sudakos. So Sudakos separation.
Yes, Hurwig has a stronger.
So accordingly harder.
Yes.
I see. But it means that you were successful in finding the Monte Carlo abstraction from Pythia as well.
Yes.
That's very good.
Yes. Yeah. So given that it's now time basically, so I'll skip the. I had a few more slides on some other processes, so you can download the talk and have a look at them. There are many, many. So I'll skip all of them. And my final summary I already mentioned just before I started the video. So you have seen that matching these next leading order calculations to Parton showers improves predictions over both leading order with Parton shower as well as next leading order fixed order results. So combining them really improves the predictions. And but it's still kind of work in progress, and there are many things that has to be sorted out. For example, Carol mentioned we want to do this matching between the 0 jet samples and the 1 jet samples, so that we can do something similar to the leading order matching, where we can match many different samples together. Right now, with this next leading order, we can just sample one next leading order calculation to the Parton shower and not higher multiplicities together with this. So there's still much work in progress here to be done. But so you're all happily invited to try to solve these kind of problems and write an interesting paper about it, of course. So yeah, so thank you for your attention.
So, questions? Yes?
So please say a few words about the WJJ.
Yes, because I have plots. So let me give you just a few words, just introduction, right? So we all know, I guess most of you know at least, that in April this year, the CDF reported this excess of events in this distribution here. Johan already showed this in his lecture as well. Basically, there's an excess of events in this region here. And then there was a great response from the physics community, phenomenology community, the understandable of the physics, more than 60 papers. Papers trying to explain it within the standard model, and also D0 tried to confirm the result, and none of this really explained it. There was also a paper studying next leading order effects at fixed order, so without Parton showering, and they didn't see any excess of events here. So what we decided to do is maybe it's an interplay between fixed order and Parton shower. So we decided to look at the dominant background here, which is this W plus jet background, and try to get this prediction at the level of Parton shower matched to next leading order calculation matched to Parton shower. So this is really a computational challenge, and this has not been done before, so it was actually kind of a complicated thing to do. But we did it in the following way. We generated 2 event samples. So the problem is actually the following. So it's easier to describe the W1 jet. That is the following. So if you use this as a Born level diagram, the problem is that if you use this as a Born, that it's divergent. You have to put a cut on the face space of this jet, or similarly on the VT of the W, to render this kind of contributions finite. However, if you put a cut somewhere at the matrix element level, you have to put this cut before you do the Parton showering, because you cannot generate your unweighted events if you don't put a cut like this. However, you have to make sure that after Parton showering, you don't get a dependence on the cut on this cut of the jet here, because the Parton shower will shift momenta around because of this it will generate more radiation, so move their position. So you can actually see this in this plot here. That what we did is we generated different cuts on this jet here. So we generated an event sample with 2.5 GeV cut, 5 GeV, 10 GeV, and 25 GeV. And then we plotted the ratio with the fixed order next leading order result. The interesting part of this curve is actually the difference between these colored lines here, the difference between these curves here. So this is just the ratio of these lines here. So if you already see that if you put a cut, for example, this green line, which is hard to see, let's start with the magenta line, which is 25 GeV, this line here. So even though the cut is at 25 GeV at the matrix element level, after Parton showering, you get many events below, therefore you miss events in this region here. So only if you put your analysis cut, this prediction is only valid when your analysis cut is much harder, like somewhere here, so you follow all these events here, much harder than the cut at the generation level. So by that, you can actually look at the difference between these lines, and you get an idea about where this cut in the analysis would be. So whereas the magenta line starts to agree with the other lines, which is somewhere here, which is around 80 GeV, you are kind of okay by having a cut test of 25 GeV to generation. So when looking at this difference between these generation cuts, you can actually get an estimate on which cut is still valid, which cut at the generation level you should use to use your particular cut at the analysis level that you're interested in. So that is what we did for W2 jets. We generated 2 event samples with a 5 GeV cut on the jets and 10 GeV cuts on the jets, 10 million events each. And then we had to validate, of course, our results to be sure that what we're doing is correct. And again, so we have these two. So we have this. This is, for example, the P of the hardest jet. So we look at these 2 event samples that we have. We have the solid line, which has this generation level cut at 5 GeV, and the dashed line has the generation cut at 10 GeV. And then we have 3 different analysis cuts at 10, 25, 50 GeV. Now this first red line here, you see that there's a great difference between the 2 predictions. And that is what you would expect, right? Because this generation cut at 10 GeV is not going to be good enough to have an analysis cut at the same 10 GeV level. So that's why you see a difference between the 2 lines, even though you make kind of the same prediction. At 25 GeV, the difference is already greatly reduced. It's hard to get. And if you look at the ratio plot here, you might say, well, it's slightly above 1, but it's almost flat. And at 50 GeV, it's okay. But then you do so much statistics that even with a 10 million event sample, you get kind of these bumpy lines here between the ratio bar. It's centered around 1, but it doesn't give you so much predictive power anymore. So we looked at different, let's say, different circles as well, in very mass, and also the angle between the 2 levels. So this was with the minimum set of cuts. So if you look at the paper by CDF, there is this list of all the possible analysis cuts that you have to implement to get the correct prediction, the prediction for your. So this is the analysis cuts that they use in this paper, and there's particularly there's a cut on the jets, which is minimal conscious jet energy to be 30 GeV. So this is kind of more than this 25 GeV before, which was already in agreement. And there's also other cuts that makes the spectrum harder and therefore better described already with the 10 and the 5 GeV cuts. There's, for example, a minimum jet air transfer of 40 GeV. And this helps to also reduce this bias on the generation level cut. So then if you look at the final results here, so this is the integrated mass with the set of cuts as by CDF and used by also by V0. We have our MC at NLO, so the next thing you want to match the particle shower result in solid red compared to the Algen results which have been used by the experimental calibration. And we also compare them with the fixed order across the sheet. And this is the ratio of these curves over the matched result here. So there's no sign of any bump around where they were seeing it in this CDF analysis. Which means that there's no, that next linear order with particle shower does not explain this excess of events seen by CDF. And then, okay, as a validation curve here, we have again this ratio of the 5 GeV over the 10 GeV generation level curve. So this is flat at 1. There's a bit of statistical uncertainty because if you use a 5 GeV sample, you lose so many events that you'll get a bit of a bumpy curve. But this is consistent with 1 as it should be. This is with the exclusive cuts. This includes the jet veto on the third jet. If you relax this veto as is done also done by CDF, you get a similar prediction here. So unfortunately, well, I don't know if it's unfortunate or not, but at least This excess of events cannot be explained by doing an next leading order calculation mentioned the Bartlett shell. So with the best predictions that we have now, which are these, they agree with within uncertainties with the rescaled Alt-Gen results. So that's very good. So that's it.
It is the most sophisticated analysis of this process.
Sorry?
So what you showed is the most sophisticated analysis today.
This today on the tutorial. No, because the reason for that is that to get these kind of curves here, you need a 10 million event sample, and so to make these plots, it just computer is already running for 10 hours. So there's no way you can do this in this tutorial. And if you use less events, you get the statistical uncertainty is too large. It just takes 10 hours to make these plots. Just the computer is running for 10 hours without even setting up the analysis.
His question is whether there is even better analysis than this.
No, this is the best prediction we have for this.
Yeah, this was
Sorry, yes.
So any other questions?
Yeah, BB bar. Yes.
Aha.
Yes. And the pulse is okay, right? There's a little bar over the BB, but not in the back. Yes. I agree.
Okay, any other error? So this remains as a mystery.
Yep.
Nice to have a mystery. Okay, thank you very much. Shall we go up and try to learn a little bit about MGraph or kind of hard.
So if you do that, That is what they can even go outside of it. That happens because in some operations the dependence on the scale at least more or less kind of artificially small. For example, just look at this model here. If you basically get the leading model, there's no outlets, there's no small positive. Therefore, the dependence on the scale is artificially small. Because the scale really enters in the strong problem. So if you vary the scales by using this as a block, you get a very, very small uncertainty. And the next leading one, the next leading one, including these diagrams and the virtual diagrams as well, is about the same order, but it's kind of off. It's not at the same value, it's rather off. So, by reasoning that here is artificially small, and you know it because there's no strong problem. So it depends on the it's not there. You know that by varying the scales you underestimate the theory. And only eventually you get it. So it's just by changing the value of the scale, you say, well, this should be cancelled by maximum order corrections, by higher order corrections, and therefore the resulting dependence should be uncertainty, estimation of these uncertainty